Today we are going to be looking at gas mixtures and real gases. If you remember in the previous video, we talked about ideal gases, and I did hint that we'll look to see if the ideal gas law applies to real situations or not. But let's begin with gas mixtures because they're very important. I mean, we live in a mixture of gases. The air in the atmosphere, it contains oxygen, contains nitrogen, contains carbon dioxide, it contains a bunch of different gases in smaller amounts. Okay, it's a gas mixture. If you go scuba diving, regardless of what they tell you, you don't get an oxygen tank. You get an oxygen and helium mixture tank. Okay, so we're going to see that the ideal gas law applies to mixtures provided they don't react with each other. They're just mixing. And basically what Dalton said was that the total pressure of a mixture is going to be the sum of the partial pressure of the component gases. So if PT is the total pressure, the partial pressures of all the components add up. And it makes kind of sense. You need to understand what partial pressure means. It's the pressure that each gas individually exerts if it was by itself. So let's say that you have a mixture that 50% is oxygen, 25% is nitrogen, and let's say that 25% is going to be helium. Okay? It's obviously that 50% of the molecules in that container are oxygen. So 50% of the pressure is going to be due to the oxygen. 25% of the molecules are nitrogen. So 25% of the pressure is due to nitrogen molecules. And the same thing, 25% of the pressure comes from helium. So really, this is a common sense law. Here you have an example where you have three separate gases, each one has a different pressure, but when you put them all together, all of the molecules are creating pressure against the walls, so you adapt the partial pressures, and that gives you the total pressure. Like I said, it's not complicated at all. Now, I was talking about if 50% of the gas is 25% of the gas. Instead of percentages, we're going to use another way of expressing the mixture, and that is the mole fraction. That's the number of moles that you have of each component divided by total number. So we can say the mole fraction in a mixture where you have A and B, the mole fraction of A is going to be number of moles of A divided by the number of moles of A and the numbers of moles of B. The mole fraction of B is going to be number of moles of B divided again by the total number, moles of A and moles of B. And now you can say that the partial pressure of A is going to be the mole fraction of A times the total pressure, and the partial pressure of B is the mole fraction of B times the total pressure. No different from what I was saying when I was talking about percentages, just a different way of expressing the composition. We can use gases in stoichiometry. It really makes no difference. There can be reactants, there can be products. It all boils down to the same thing we did with the stoichiometry. Change it to moles. If you remember, we had that overall chart, and I added myself. I said, if you have a gas, you're going to have pressure, volume, temperature. You calculate number of moles, then you use the mole ratios to calculate the product, something like that. Or if you have moles of product, depending on what they give you, you can calculate the pressure or the volume or the temperature. They will give you two, you calculate the third one. It's exactly the same thing. You just change what they gave you. If it was a solid, they gave you grams, you change it to moles. If it was a solution, they gave you concentration and volume, so you calculate grams, change it to moles. If you have a gas, they give you pressure, volume, and temperature, you change it to moles. It's exactly the same thing. The only reason we didn't spend a lot of time doing examples with gases is because we haven't covered gases yet. Okay? You did not know the ideal gas law, but it's exactly the same thing. For instance, look at propane. Now, propane, you're using gas grills, and they tell you at this temperature and at this, and obviously they're going to say this is 1 atmosphere. This is going to be 25 plus 273, so 278 Kelvin. and they want to know how much oxygen does it take to react with this volume of propane. There's two ways you can do this, and either one is correct. So really, it's your choice. You could say, okay, propane. I had the volume of propane, I had the temperature of the propane, I had the pressure of propane. So using PV equals nRT, I can calculate the number of moles of propane. Then I look at the mole ratio and say that I have to multiply times 5 because there's 5 moles of oxygen per mole of propane. Now once I have moles of oxygen, temperature of oxygen, pressure of oxygen, I use PV equals nRT, and I calculate volume of oxygen. That is the long way, but on the other hand, it's all stuff that you already know that you should be able to do without any difficulty. Or you can say, hey, the temperature is not changing, the pressure is not changing, so we could just compare volume to volume. Remember when we said put everything that changes on one side, and basically you're saying the pressure, the volume, the number of moles, R doesn't change. Sorry, I meant temperature. Let me just, sometimes when I hurry up, PV equals nRT. So number of moles doesn't change, R doesn't change, temperature doesn't change, P. So we can compare the volume. You can compare the volumes before and after. Now you see from the number of moles, well actually the moles does change, multiply times 5, so the volume is going to be multiplied times 5. You can just compare volumes of oxygen. Either way, this is supposed to be shorter, this is safer. And if I was you, I'd go the safe way anytime. There's a couple of definitions we need to add in here. Diffusion is how gas molecules disperse. Remember, gases occupy the total volume. Okay, so in this particular case, we have hydrogen on one side of this container, oxygen on the other one. There's a stopcock that's closed. When you open it, some oxygen is going to be moving to the left, some hydrogen moves to the right, until the concentration of both sides is even the same. You have the same amount of oxygen, hydrogen on both sides. Notice that during the process, hydrogen moves faster. You have 1, 2, 3, 4, 5, 6, 7 hydrogen molecules, and only 4 oxygen have moved. Because diffusion rates depend on several factors. It depends on the temperature. The higher the temperature, the more energy molecules have, the faster it goes. The mass of the atoms. The heavier the atom, the slower it moves. So hydrogen is light. H2 weighs about 2 grams per mole, so it moves very fast. Oxygen is going to be 32 grams per mole. It moves slower. So the mass of the atoms depends on that. Concentration gradient, I like to compare if you have a steep hill and a very easy hill, and you get on top of it on a little red wagon. Which red wagon is going to go faster at the bottom of the hill? The one with the steep hill is going to go faster. Common sense. Same thing, when you have a steep concentration gradient, the molecules move faster. Okay. Effusion, on the other hand, is the movement of gaseous species, but when you have a pinhole, so they can only move one molecule at a time. Okay. We said both for diffusion and effusion, the rates depend on the molar mass. The rates are obviously not going to be equal, but the ratios of the rates are going to be the same. This is very useful when you're trying to calculate molar mass because of Graham's law of effusion. And I don't expect to memorize, but the rate of effusion is inversely proportional to the square root of the molar mass. So you have two gases, A and B. You can measure the rate of effusion. You know the molar mass of A, for instance, so the rate of effusion of A divided by the rate of effusion of B is the square of the molar mass of B, remember it's inversely, divided by the square of the molar mass of A. If this one and these ones are determined experimentally, and you know this one, you can calculate the molar mass of B. So that has been used, okay? I'm not going to spend much time in that because it's kind of an old technique. An easy way to explain is to have you have two balloons, helium balloons, rubber balloons. One is going to contain helium and the other one contains argon. If you look at the periodic table, helium's in the first period, argon's in the third one. It's a bigger, heavier molecule. So you wait a few hours, and what happens? A lot of the small molecules of helium escape through the pores in the rubber. So the helium balloon becomes smaller, but the argon is bigger, it comes out slower, so you really cannot tell the difference. That's pretty much the reason we use now Mylar balloons for helium, because rubber did not contain the helium very long. Can't tell you when my children were little how many times we come from a party with a helium balloon. And the next morning, the helium balloon is lying on the floor. And she's small. Mom, the helium balloon is dying. Don't worry. I'll take it out in the jar, make sure it was secure, left it in the sun, go out in a few hours, and the helium balloon was flowing again. And sure enough, yes, it had less molecules of helium that had escaped, but when you increase the temperature, you increase the volume. And sometimes you could do it 2 or 3 times before there was so very little helium that didn't make any difference. We said that ideal gases can be explained by the kinetic molecular theory. So let's go over what are the 5 postulates of this theory. We're going to see that some are questionable, okay? Gases are composed of molecules that are in constant motion. Yes, that's true. We know they travel in straight lines and they only change directions when they collide with each other, when they collide with the walls of the container. That's fine. The molecules composing the gas are negligible compared to the distances between them. That would be like almost saying that the molecule doesn't have any volume. So let me just call it so-so. The fact is, gas molecules does have a volume, and even though there's plenty of empty space, can you consider that negligible? We'll see, okay? The pressure exerted by a gas results from the collision between the gas molecules and the container walls. Agree? Gas molecules don't attract or repel each other. That means that their collisions are elastic. There's no loss of energy. Because if they stack to each other, then you have to use energy to separate them. Right? But is it true that there's no attractive or repulsive forces? We're going to see in the chapter on intermolecular forces that that's not always true. Sometimes it is, sometimes the attractive forces are negligible, sometimes they're very significant. Depends on the gas. So let's just call that so-so, depends, whatever you want to call it. And the average kinetic energy of a gas molecule is proportional to the Kelvin temperature. Yes, we agree, the higher the temperature, the higher the energy of the molecules. So there's a couple of questions in here, and we are going to address that and see what difference it makes. But first, I want you to see that the kinetic molecular theory explains the behavior of the gases. Okay? For instance, you have a gas in here, you add heat, but the volume does not change. Well, obviously the molecules are moving faster, so the collisions are stronger, that increases the pressure. Okay, so you have molecules, and now you decrease the volume. You have the same number of molecules, less volume. That means there is less surface, so the number of collisions per unit of surface is going to increase, because it's the same number of collisions, but less surface. So the pressure increases. Or you have a number of molecules, and you want to maintain the same pressure, but you add more molecules. Well, the only way the number of collisions per surface area does increase is by increasing the area. So that means that volume increases. So the kinetic molecular theory explains what we have seen with ideal gases. But gases, real gases, are not ideal gases, okay? We are going to see that there are differences. And this book chooses as an example the compressibility factor. Basically, we say 1 mole of an ideal gas at the standard temperature and pressure is 22.4 liters, right? 1 mole, 22.4 liters at standard temperature and pressure. But what if you actually measure it? It's going to come up with a different number for a real gas. If the actual gas, the real gas, was identical to the ideal gas, their two volumes would be the same, so the factor would be 1. But you can see in the examples, nitrogen, methane, hydrogen, oxygen, they're not 1. So real gases are not ideal gases. Now, how significant is that? Let's see. The problem that we have is the attraction between gas molecules. We are going to see, like I say, in intermolecular forces, that some gas molecules attract each other. So the pulling molecules closer together, they're going to affect the volume. Okay? They decrease the gas volume. That's also going to decrease the force of the collisions because some of the energy is being spent breaking down those attractive forces, so they reduce the pressure. Basically, real gases should have less volume and less pressure than ideal gases. Now, is that significant? Well, van der Waals decided that he was going to come up with an equation to replace the ideal gas, and this is I don't expect you to memorize it, okay? But I want you to understand that you correct the pressure for molecular attraction and you correct the volume because of the volume of the molecules. The molecules have volume, okay? So those letters A and B, van der Waals spent a lifetime determining those values for every gas he could come up with. So they are in tables and you can correct them. Now, I think I mentioned in the previous video, we was isolating hydrogen in the chemistry lab. We calculate the volume of the hydrogen, and then I said, let's correct the volume and the pressure, or just the volume, we did only volume, but let's correct the volume by the factor that represents the volume of the molecules. You go to the table, you find out how much is B for hydrogen. We knew the number of moles because that was part of the calculations. And you know what? When we did the correction and we put the number with the correct number of significant figures, we came up with the same number. Coincidence? Maybe, but on every semester at that college, we had between 800 and 1,000 chemistry students. When more than 800 students come up with it didn't make any difference, you pretty much can assume that the ideal gas law is going to work just fine for college chemistry. Now, you're going to be a specialist in gases. No, you will have to use van der Waals equations. But for this course, this equation works just fine. You don't have to worry. Okay? So this was a very short video, but once again, if you want help one-on-one, if you want to see any of my worksheets, and I do have some worksheets that involve mixtures of gases, you know what to do. Go to the video description, click on the link to my Waals account, make an appointment, and you will get the worksheet, and I will go over it together.